camera models, and we define the intrinsic parameters of the camera. Let's now turn to the extrinsic parameters. So when we derive the intrinsic parameters of the camera, we assume that the coordinate system is at the pinhole of the camera. Remember that? So if I have, say, this image plane right here, and this is my box, and I have a pinhole right here, I assumed that my coordinate system is located at the pinhole. But in reality, I work in the three-dimensional world, and my coordinate system is here somewhere, right? So I have to find a relationship between these two coordinate systems. And as we saw in the last lecture, this is defined by a rotation and a translation, right? Such that we have the point, our three-dimensional point capital P, as defined by the camera coordinate system, which is this camera coordinate system here. So remember, this is written down as a C, or capital letter, for the coordinate system that I'm using on the top left corner of the variable P. This is equal to the rotation from this other coordinate system, which I'm going to call the world coordinate system, to the camera coordinate system, times a translation, times a row of zeros and a 1. Now, this translation, we know what this translation is. If we call this origin right here OW, then this is going to be OW as seen from the coordinate system of the camera, right? Yep. All right, excellent. So now I need to combine this equation with the equation that we derived in the last lecture of the intrinsic parameters. So I'm going to create the matrix M. There's going to be K times R T, where T is equal to OW as seen from the camera. R here is our rotation matrix from the coordinate system of the world to the camera coordinate system. P is obviously our point as seen from the world, so we can write XW, YW, ZW. And the image point P, small p now, right? So whatever image point small p I may have here, small p is going to be equal to 1 over Z times MP, right? Let me call this P for simplicity, and then delete the W. So that here, remember K is the matrix of intrinsic parameters. And that equation here, that defines the perspective projection camera. Okay, any questions thus far? We understand intrinsic and extrinsic parameters of the camera? Okay, so now this M that I've defined here, obviously it's a matrix that has 3 rows. Let me call these rows M1, M2, and M3. These are the 3 rows of capital M. And small p, remember this is small p, we called it earlier UV, the 2 coordinates. And therefore I can write that U is equal to M1 transpose P, capital P that is, over M3 transpose capital P, and V would be equal to anyone? Just using this equation. Very good. M2P over M3P, right? M3 transpose P obviously corresponds to Z. M1 transpose P corresponds to that part of the projection, right, of the first row, and M2P corresponds to that other part of the projection here that corresponds to the V or the Y component, right? And again, this is our perspective projection equation. This is exactly the same equation we saw before, where we had 1 over Z or F, if you want to include the focal length, 1 over Z X and 1 over Z Y, right? Same thing. So you can put everything together. So let's review what we had. K, remember, K was given by our projection matrix, which was alpha negative the cotangent of the angle of our physical retina, and U0 was the shift of the central point, the projection of the pinhole in the physical retina to whatever we define 0, 0 be in our image. Beta over the sine of the angle V0, 0, 1, right? That was our case. So if we now combine everything together, as in this, we get M, which is equal to, let's see, alpha times R1 transpose minus alpha the cotangent, whoops, hold on, there's another column, negative alpha the cotangent of theta R2 transpose plus U0 R3, and then the other column is alpha Tx the cotangent of the angle Ty plus U0 Tz. Here I have beta over the sine of the angle R2 transpose plus V0 R3 transpose, and beta over the sine of theta Ty plus V0 Tz, where obviously I have defined T to be Tx, Ty, Tz, right? And my matrix R, that remember was defining the rotation as R1 transpose, R2 transpose, R3 transpose, defining the 3 rows of my rotation matrix. Now I'm going to call this first part of my matrix A, And that second part of the matrix right here, B. All right. B, okay? Such that I can write that M is equal to A, B, okay? Now, A, it's a 3 by 3 matrix, and B, it's a 3 by 1 vector, right, or a 3 vector. Any questions? Question? Am I here?
First row at the end. Now RQ.
Oh, R3. My mistake. Thank you. Thank you. Now, again, I know I keep repeating this. All these equations are in the slides and in the book, right? So you don't really have, I don't think you have to write it down. I mean, you're welcome to write it down and definitely correct me if I made a mistake, but I wouldn't waste my time writing it down, but rather try to absorb that information and understand it. All right, any other questions? Okay, so remember from day one, when we define perspective projection, right, that we have u it's equal to x over z and v equals y over z. That was in non-homogeneous coordinate systems. This is the exact same thing right here in homogeneous coordinate system, right? What does this mean among many other things? That implies that this solution is defined, anyone? Up to scale, right? So that M here is defined up to a scale. That's very important to remember. So that if I change M by lambda M for any lambda different than 0, right? That's still an equally valid solution. And that's apparent here in these equations, isn't it? If I multiply by a scalar and divide by the same scalar, I'm not doing anything, am I? Right? Now that will be very important when we work with these camera models to define both the camera and the 3D world. We will only be able to do so up to a scale, right? So for example, for an object, if I'm trying to reconstruct an object like this, right, from an image, I'm going to be able to reconstruct its shape, but from a limited number of information, I'm not going to be able to determine its exact size, because the size is going to be defined up to scale. Okay, so obviously M is not usually known. I mean, sometimes it may be known if you know the exact camera that you are using and you know exactly where is it placed, it may be known, but in general it's not known, it's to be estimated, and that's something that we will start working on very soon. Before we can do this, maybe it's important to note that some of the parameters in that matrix M, these are the parameters that are shown here in this equation, may be assumed or may be fixed to some specific numbers. For example, it is quite common to assume that the camera is what's called zero skewed. Okay? That means that we assume that the angle theta in the physical retina, it's actually 90 degrees. Okay? In that case, we say that M is a zero skew perspective projection matrix. It is also sometimes, or very common actually, to assume that alpha is equal to beta. Remember, those are the parameters that determine the size of the pixel, right? So obviously the pixel is not a square. Remember that? It's 1 over alpha by 1 over beta, but, or 1 over k by 1 over L, and alpha and beta are multiplied by the focal length, right? So it is actually very common to assume that they are the same. And in that case, we talk about a perspective projection matrix with zero skew if it's assumed to have 90-degree angle in the physical retina, and unit aspect ratio. How are we going to know that? That's given by the following theorem. We'll say let M be our matrix AB, right? So a 3 by 3 matrix A and a 3 vector B, or rather a 3 by 4 because we have the row of zeros underneath, right? So 3 by 4 and a 4 vector. And AI transpose the rows of this matrix A. Then, if the determinant of A is different than 0, then, and that's an if and only if, M is a perspective projection matrix. If the determinant of A is different than 0, and that, by the way, A, we already stated this in our last lecture, right? A has to have a determinant that's different than 0. Otherwise, that does not define a perspective projection, right? Now, if in addition to the determinant being different than 0, then the inner product of A1 cross product A3 with A2 cross product A3 is equal to 0, then, and again, this is an if and only if, M is a zero skew perspective projection matrix. Now, this is given by, again, the cross product of A1 and A3, which gives me the other direction, with the inner product of A2 and A3, and they have to be equal to 0, meaning they have to be orthogonal to one another, right? And that only happens if you look at this equation that we have here, right? That can only happen when the angle theta is actually 90 degrees. And finally, C, if the determinant of A is 0, and this condition also holds And we have A1 cross product A3 inner product with A1 cross product A3 is equal to A2 cross product A3 and A2 cross product A3. That is the norm, the true norm of the vector that I obtain when I do A1 cross product A3 is exactly the same as the norm of the vector obtained when I do A2 cross product A3. Then that can only happen when the aspect ratio of the camera is unitary. So then this is a zero skew unit aspect ratio perspective projection camera. Okay? I'm going to skip the proof, shall we? All right. Well, let's skip the proof. Any questions? That's how you know which type of camera you have, okay? If it's a perspective projection camera. Now let's go back to affine cameras. Let's use this type of modeling to define the affine cameras that we introduced early on in the course. We already know about the orthographic camera that we introduced, right? Remember, if I have my image plane, this is my image plane. Now, I could draw the image plane like I did before, like this, right? This is a very typical way to draw an image plane, trying to draw a plane in 3D. Now you will see that most often than not, people are uncomfortable drawing this, so just draw a line. What this is mean is, if this is my image plane, I'm just drawing that line, okay? So I'm showing the image plane orthogonally to the plane that it's on your view. That makes everything much easier to draw. So we already saw this orthographic projection. And if I have an object here, right, a 3D object, then this is orthographically projected, meaning 90-degree angles here, right? Orthographically projected, and what I obtain here is my image, right here of the object. But orthographic projection has a problem, which is if the pinhole, my pinhole is right here, right? This is my pinhole. Then the orthographic projection gives me a weird projection off center, right? There is another projection, which is called parallel projection. Which what it does is, for the same object, it takes into account where the pinhole is, okay? So if the pinhole is right here, what I'm going to do, or actually, let me do it like this. If it's right here, what I'm going to do, I'm going to first project this point, some reference point right here, okay, to the image plane through the pinhole, right? So I get the small r. And then every other point is going to be projected such that this projection is parallel to the reference one. That way, I obtain here a representation that is centered or closer to the center of the pinhole. That can be extended to what's called the weak perspective model, which is extremely popular. This is super popular. Weak perspective model, which works as follows. So imagine this is my image plane. This is my pinhole right here, where the origin of my coordinate system is. And then here I have some three-dimensional object. And now I have to project 3 points from my object. Let's say these 3 right here. So I have R, P, and Q. Okay? Now R, as before, is going to be my reference point. So R is going to define my reference point, and it's going to give me this projection. So a small r corresponding to the image coordinates of the real point, capital R, going to be these ones. Okay? This is done with perspective projection, okay, through the pinhole. Now, I'm going to project every other point before I project it using perspective projection to here. I'm going to project them orthographically to that reference plane that is parallel to the image plane located at R. So I'm going to project this here and here orthographically. Okay? And then once I have this new point, let's call it P prime and Q prime, I'm going to project these two through the pinhole to get small p and a small q. So this first projection is orthographic projection onto the reference plane. This reference plane is defined at a distance of ZR, right? So R is obviously XR, YR, ZR. So this is at ZR distance from the pinhole, right? In fact, negative ZR if you prefer. No, actually positive, right? Because we said Z direction, yeah, positive ZR. And once we have this orthographic projection, we use perspective projection to project these other points onto my image plane. Okay? Very popular model. We'll be working with that model a lot. There is one more that is worth mentioning. It's not very popular. It used to be, which is called paraperspective model. Which is a combination of the weak perspective and the parallel projection. So instead of doing orthographic projection first, I'm going to do parallel projection first, and then perspective projection. Okay? So let's see how that would work. So I have my image plane, my pinhole, my three-dimensional object, and I have, as before, R, P, and Q. So I'm going to define R as my reference point as before. So that goes through the pinhole using perspective projection to get me small r. Now P is going to be a parallel projection, parallel with respect to that projection, right? So I'm going to do parallel projection. So, well, I guess I can do better than that. And this one is parallel to this. Oh, still not that great. Huh? Okay, it's a little better. And once I have this P prime, now I'm going to use perspective projection to get small p. And I'm going to do the same thing here. I'm going to do this parallel to this to get Q prime. And now I'm going to go through the pinhole to get me small q. Okay? See how this works? All right, so now let's define the matrices, shall we, in homogeneous coordinates. So as always, we start with our three-dimensional point, x, y, z1. This is our three-dimensional point in homogeneous coordinate system. And our small p in perspective projection, which is 1 over z mp. In weak perspective, right here, what we do is note we take x, y, z1, and we first project everything orthographically to the reference plane. What would that be equal to? If I project x, y, z1 to the plane defined by R, what am I going to obtain here after this orthographic projection? Is x going to change? No. How about y? Is y going to change? No. Good. How about z? Z going to change? You want? Yeah. Where is it going to be? ZR. Excellent. And 1. Very good. That's the orthographic projection, right? This first orthographic projection here. And now I'm going to apply perspective projection on that. And what's perspective projection is going to get me my u's and v's. Let's call them u hat, v hat, because they have changed, because now I have zr, right, instead of z. So that I can write, if you will, we could write x over zr, y over zr1. Now we want this in matrix form, as always, so I'm going to write u hat v hat 1 is equal to some matrix, right, times x, y, z, and 1, right? Okay? All right, so let's see. Why don't I do this? I'm going to take 1 over zr out here, because this is what we like to do, right? 1 over z. So 1 over z, I'm just going to take it out here. Now, the first u is defined as x over zr, ZR array, have it here. So I need 1, 0, 0, 0, right? Excellent. How about the second row? Anyone? Jet? 0, 1, 0, 0. Very good. And how about the last row? Okay, 0, 0, 0, 1. Excellent, right? Because that's going to give me the one that I'm looking for, right? Excellent. So note that there is here a column of all zeros. What does this correspond to? To Z, because I'm not using Z. I'm only using my reference ZR, right? Okay. Great. Now, to complete this, we obviously need to include the external parameters, right? The rotation and translation. So now let's add this to this equation. So I'm going to do this right here. So I have uv1 is equal to 1 over ZR k times 1 0 0 0 0 1 0 0 0 0 0 ZR. Oh wait, this was incorrect, right? That should be ZR. Oh yeah. You have to correct me if I did get it wrong. This should be ZR, right? So ZR over ZR is equal to 1, right? Okay. Times our rotation, translation, zeros and 1, and then x, y, z1. Okay. So now here I can have my intrinsic parameters, and here my extrinsic parameters. Right? As I had before, I have a rotation and a translation, right, as before. And usually I'm going to simplify this, my K matrix, as KS01, this is small k, this is capital K, right? Where KS correspond to the skewness of the camera and the aspect ratio of the camera. Note also that we don't have in this equation U0, V0. It doesn't make any sense for us to rectify for U0, V0 because of the orthographic projection that we apply to ZR, right? That actually eliminates the uses of that image center. Also note from this equation that if I translate the object or the points on the object in the z direction, that is not going to have any effect in the projection, right? The only point that matters is the reference point. Everything else is irrelevant. For the z direction, I mean. All right. We could repeat the same for the paraperspective camera, but instead of doing that, I'm just going to give you the end result, and you can do that at home to practice how to model cameras. the model that you will get if you repeat exactly what we did, but when we use the orthographic projection, use the parallel projection instead, you're going to get M equals 1 over ZR KS01. Remember, this is the skewness and the aspect ratio of the camera. 1001 XR over ZR YR over ZR RT. We'll note that now we have this new term here, right, that I have right here, that has changed, and that's the one that defines the parallel projection instead of the orthographic projection. Okay? All right, any questions? So let's, if there are no questions, let's see how we can now estimate the parameters of these camera models, right? So these camera models have a number of parameters. If I knew the value of these parameters, then I know how my camera works, right? And why do I want to do that? Well, because if I understand how my camera takes pictures of the 3D world, then I understand what my 2D images correspond to in the 3D world, right? So if I know how to go from 3D to 2D, I automatically know how to go from 2D back to 3D, right? All right, so let's see how we can estimate the parameters of my cameras. And for that, this is called geometric camera calibration. And for that, we're going to define a method that's going to be very useful for us for a big portion of this class. I sometimes joke that this class should be called linear least squares instead of image processing. You'll see why. Okay, so okay, so we have our camera, pinhole camera model here with the little pinhole, the origin of the pinhole, and the coordinate system pointing toward inside the camera, right? So this would be the center of the image with where the pinhole is projected. And this is the physical retina or image plane. And then somewhere out here, there's the 3D world, right? Now the problem is that any point in 3D world is 3D, any point in the camera, it's 2D. How can we find point correspondences that allow us to derive a number of equations that give us the parameters or solutions to the parameters of the camera? What we're going to do, something very smart, we're going to use a very specific type of object that's called a calibration grid that looks like this. It has vertical and horizontal lines at the specific distances from each other. And it has three planes that are orthogonal to one another. So I have a plane right here that defines this surface, right? Another plane right here that's orthogonal to this one, and another plane right here that's orthogonal to both of the previous ones, okay? Now I'm going to place my coordinate system of the world right here at the intersection of these three planes. And the coordinate system, obviously, it's going to be right here. These three lines defining the union of every two pair of planes are going to define my basis vectors of my three-dimensional world coordinate system, okay? Now, because that union of the three planes is my origin, meaning 0, 0, 0, and I know that every vertical line and horizontal line are at equal distance, say 1 centimeter or 1 inch or what have you, then I automatically know the three-dimensional world coordinates of every single intersection of horizontal and vertical lines in that object. See how this works? So if you were to come here, so this, let's say x, y, and z, then you go here, you know, oh, this is 1, 1, 0, this is 0, 0, 0, 1, 1, and this one is 1, 0, 1, right? And so on. For every point in that object, you know its coordinates. Now, if you take an image of that object, you have the UVs of that object for every point in that object, right? So let's write this down. Let's write this in an equation. Oh, there it is. So I'm going to get UI VI for my point PI here, right? So this point here, capital PI. And can anyone remind me what the equations of perspective projection are? What's the equation of UI? Anyone? Okay, M1 transpose PI over? Very good. And M2 and M3, right? So let's write this down as a system of equations. So all I'm going to do, I'm going to move this to the other side. So I have M1 transpose minus UI M3 transpose times P equals 0, and M2 transpose minus VI M3 transpose times P equals 0, right? Correct? That should be PI. Right? Yep. Okay. Next one. So from these equations, what are my knowns and what are my unknowns? Is M1 known? Nope. Is UI known? Yep, okay, so let me actually change the color. So this is known. How about M3? Nope. How about P1? Yes. No? Yes, P1 is known, right? No, exactly, it's three-dimensional coordinates. How about M2? No. V1, yes. M3, no. PI, yes. All right, so we have equations with a number of knowns and a number of unknowns, right? So I need enough equations to have more knowns or more equations than unknowns, and then I can solve it, right? How am I going to solve it? Well, for this, we need to define a method, and that method is called linear least squares. So let's see how this works. Linear least squares is used to solve problems of that form: u11x1, u12x2 plus u1q xq equals y1, all the way, well, let's do one more. u21 x1, u22 x2, u2q xq y2, all the way to p equations: p1 x1, p2 x2, pq xq yp. Okay. So if this system of p equations and q unknowns, excellent. All right, this is a very generic form, right? x1 through xq, these are my unknowns, and uij's are my knowns, right? My coefficients, okay? They're known to me. So let's see an example, just to clarify. Imagine the following example: x1 plus 4x3 equals 3, 2 times x2, whoops, 2 times x2 plus x3 equals 4, and 3 times x1 equals 1, right? So that's the type of system of equations that we're talking about. Okay? So far, so good. This is just a very simple example. You've seen this for many years, I hope. But let's write this in matrix form, because we like to write things in matrix form in this class. So let's see how this works. I write 1, 0, 4. These are the coefficients of my first equation for x1, x2, and x3, right? So x1 has coefficient 1. x2 is not in the equation, so has a coefficient of 0. x3 has a coefficient of 4. The second equation would be 0, 2, 1. And the final equation would be 3, 0, 0. Now, I need to multiply this by my unknowns, x1, x2, x3. And this is equal to 3, 4, 1. Correct? Let me call this matrix capital U. This is the matrix of the coefficients that are known to me. This vector, capital X, or vector X, if you prefer, and this vector, vector Y. And that way I can write ux equals to y where u, in general, right, in the more generic case, this one that we have written here, would be u11, u12, all the way to u1q, u21, u22, u2q, and p1, p2, pq. Okay? X in general, this x, this vector x, would be equal to x1 through xq, and y would be equal to y1 through yp. Now, the rank of u is going to be smaller or equal than the minimum of the number of rows and columns, P and Q, right? Right? So if I have a 3 by 2 matrix, the rank cannot be larger than 2. You agree? Okay. So for simplicity, let's assume that all my equations that I have in the system of equations are linearly independent, right? In that case, I can say that this is going to be equal to the minimum. Again, if the equations are linearly independent only. In that case, let's consider the following cases. What happens when P is smaller than Q? Anyone? What happens if P it's a number of equations, right? I have less equations than unknowns. What happens? There are no solutions? No. There are an infinite number of solutions, right? Specifically, the number of solutions are defined in a Q minus P dimensional space. Right? To see this, note that each equation provides enough information to find the exact value for one of our unknowns, xi. Right? Each equation gives us enough information to solve for one xi. If I have, what did I say, P equations, then I can fix pxi's. The ones that remain, which is Q minus P, those remain unknown. I can never fix them, right? So for example, let's see an example. Very simple example to clarify. Imagine you are in 3D, 3 dimensions, and this dimensions corresponds to x1, x2, and x3 right here. Okay? And you're given the following system of equations: x1 equals 3, x2 equals 2. Very simple system of equations. What does this mean? It means that x1 is always 3, right? x2 is always 2, and x3 can take any value. What does it mean that it can take any value? It means that it can take any value in that direction or in that direction, right? Okay. And this is a one-dimensional space, right? A solution space, a one-dimensional solution space that specifies all the possible values. Okay, this is the first possible case we can find. Now, what happens in my second case, again, remember we're assuming that all the equations we have are linearly independent. What happens if P is equal to Q? There's what again?
Only one solution.
There's only one solution. Okay, there's a unique solution. Perfect. Right? Obviously. I mean, we can give an example here. There you go. 3 equations, 3 unknowns. Now we have a unique solution. Okay. Now, what happens if P is larger than Q? There is no solution. Great. I cannot emphasize this enough. There's no way there can be a solution with my example here. Let me give you another linearly independent equation. Let's see, x1 equals 7. Right? If it has to be linearly independent, there's not going to be a solution, right? It's impossible to have a solution, just one. All right, that's the case that interests us the most. Because in general, what we're going to do here or in pretty much everywhere else in the class, or the first 1/3, 2/3 of the class almost, what we're going to do is we're going to have generally more equations than unknowns, right? The number of unknowns for the camera models that we have defined varies between 5 and 12, right? But the number of points that we're going to use here is going to be in the dozens, hundreds, if possible, even thousands in some cases. So we're going to end up with potentially dozens of or even hundreds of equations and 12 unknowns, right? Now, because both things, I'm going to make errors when I estimate my values in the real world. I'm never going to be precise to the millimeter, right? Or to the nanometer. And second, my model, my camera model, is only an approximation of the real camera. Then I want as many equations as I can, because my solution is never going to be perfect anyways. But the more equations I have, the better I can approximate to something that works better in the real world, right? But the problem I have is I cannot find a solution. Or can I? That's when least squares comes in. So let's see that. Let's see how we can do that with least squares. So what we're going to do is we're going to define an error function, okay? We're going to define a new error function that describes each of these equations, right? So let me write the ith equation in that system of equation as ui1 x1 plus uiq xq minus yi. Now this can either be positive or negative, right? It can be a positive number, it can be a negative number, because I'm subtracting y. I could take the absolute value to make it positive, but you will see shortly that I need to compute the derivative of this. So just to make it differentiable, I'm going to compute the square, which solves the same, it's the same problem, right? Solve the problem. And I'm going to add from 1 through p. Is that what we said? Yeah, p. I can rewrite this. This is the same as writing u, the matrix u that I have defined over here, right? times x minus y squared, right? Same thing. I can write it in matrix form if I prefer. Now what we want to do is we want to find the solution for x, because u and y are given, those are knowns, right? X is my unknowns. I want to find the solution for x that minimizes that error function e. Okay? So I want to determine the x that minimizes my error function e. Okay, let's see how I can do that. Now, if I want to find the value x that minimizes this function, this error function is nothing else than a function, right? So for a certain values of x, so let's assume that x is only x1, right? Just one unknown. Then the error function is going to take certain values, right? And I want to find that zero, or that inflection point where the derivative of the error function is actually equal to 0. And I want to make this with respect to each of my unknowns. So I want to equal this to 0. Now, the partial derivative with respect to xi is equal to, let's see, e. Let me call this e, small e squared. So I can do now 2 times the partial derivative of e with respect to xi, which is equal to, let's see, it's going to be 2. Now the partial derivative of e is going to be the partial derivative of c1 through cq, where this is my matrix U, right? So C1 is the first column of U, CQ is the last column of U, times my vector x1 through xq minus y. And what's this equal to? This is equal to, let's see, if I extend this, I get x1 times c1 plus all the way to xi ci and xq cq minus y. And what's this equal to? Let's see. I'm deriving with respect to xi, so this is 0. This is 0, everything is 0 except this one, which is ci, right? Okay, so that means that if I have this partial derivative equal to 0, then I have ci transpose times ux minus y equals 0, right? And this comes from this equation right here, right? And therefore, I have, now this is ci for the ith element. Let's apply to c1, I equal to 1, c2, I equal to 2, and so on up to the last one, times ux minus y, and this is equal, what's this equal to, anyone? C1 transpose, C2 transpose, CQ transpose? Yes, U transpose, very good. So this is U transpose times UX minus Y. All right, excellent. This is equal to 0. So now I can move things around. So I'm going to do U transpose UX and U transpose Y. Okay? Going to move one to the other side. So I have U transpose UX equals U transpose Y. And now X, which is my unknown, is going to be the inverse of this. Move to the other side. U transpose U inverse U transpose Y. All right. And this matrix right here it's called the, anyone knows this? The pseudo inverse. Very good. Now, U, obviously, we erase this, but U is U11 through U1Q, and then UP1, UPQ, right? So P by Q is not a symmetric matrix. I cannot invert it. If I could invert it, this equation right here, which was UX minus Y equals 0, that has an easy solution, right? I move Y to the other side, I invert U, I have X. But U cannot be inverted, but what we've shown with these derivations is that there is a solution called the pseudo-inverse, which is this one, that allows us to do it. Okay? Now, this is not exactly what we have, because remember that we now work in homogeneous coordinates, right? This is in non-homogeneous coordinates. Now we need to repeat the same thing for homogeneous coordinates, okay? So let's see what the least square solution is for homogeneous in a homogeneous coordinate system. All right. List the squares. And in homogeneous coordinates. All right. Or in homogeneous systems. All right. This is the same as this one that we have here. You see the system of equations, but with a small tweak. All we need to do is change these yi's for anyone? Zeros. Good. Right? That's it. Now these are homogeneous equations. And now I have the same I had before, capital UX minus Y, which is a vector of zeros, which I can ignore, equals 0. Okay, in this case, if P is larger or equal than Q, non-trivial solutions, and we call them non-trivial because there's a trivial solution here, isn't it? That we didn't have before. X equal to a vector of zeros, that's right. That's called a trivial solution. It's completely useless, but it's a solution, right? Okay, so non-trivial solutions, meaning non-zero vectors, may only exist when U is singular with rank strictly smaller than Q. Okay. In other words, that's the same as saying that minimizing our error function that we've defined before, that now is ux squared, only makes sense when we have or we add additional constraints. Why is that? Anyone can remind me why this is? Why do I need an additional constraint to make sense of my solution? What's that? Because if X is a solution, let's say that X is a solution, right? Then what happens? Can I find any other solution other than X, if X is a solution? Right, so very good. Lambda X, it's also a solution for any lambda different than 0. Still a non-trivial solution. So in fact, I have an infinite number of solutions. Even in that case, I have an infinite number of solutions, right? So a solution only makes sense if I add an extra constraint, such as one constraint that we can work with is that the norm of X is equal to 1. Now, if I fix the scale, the solution makes sense because there is a unique solution, because I have fixed the lambda. Okay? Now, because I have ux squared, this is equal to X transpose U transpose Ux, right? And now I have U transpose U, which is a symmetric matrix by definition, and it's positive semi-definite, meaning that all its eigenvectors and corresponding eigenvalues are positive or 0. And therefore, okay, did I call it a special name? A. Okay. That matrix, let's call it A. I can compute the eigenvectors of A to obtain both my eigenvectors, V1, wait, hold on, here I call them V1. I don't know, it's okay. V1 through VQ and the corresponding eigenvalues lambda 1, lambda q, okay? All right, any questions? All right, now we can see how we can apply this, for example, to find the best fit of a line, or later a hyperplane, to a set of vectors that we are given in RP. And I'll do that next time. See you then. Actually, just very quickly,